Welcome back. In this video, we'll look at a very common probability distribution function. This is called the Gaussian distribution. Many of you would have seen this before. This is a very commonly used function within science and engineering and even in mathematics for several unique properties that it has. One of the most useful properties is something called the central limit theorem, which I'll talk about very shortly. It turns out that the average of almost any independent distribution over multiple realizations, if it's added together and if it's averaged together, it tends towards the Gaussian distribution. And this is what makes it occur again and again and again. Now, again, unfortunately, we won't have the time to go through the nitty-gritties of the Gaussian distribution. We are going to more or less use it as a tool, but I'll just briefly introduce it. Apart from the Gaussian distribution, there are several other practical distributions that exist within probability. There is, for example, the exponential distribution. There are several other distributions that can be used, very usefully used. But what you should see the Gaussian distribution is as a model for the PDF of any function. As we will see shortly, well, we will not really see it, I'll just say it. It makes sense to use especially the cumulative distribution function, what is called the CDF of the Gaussian to make predictions about the likelihoods of events. So CDF stands for cumulative distribution function. And in many ways, the cumulative distribution function is more useful, more practically useful than the probability distribution function. Essentially, the cumulative distribution function is simply, so if you have a probability distribution function like this, then the cumulative distribution function, so let's say integral of p of x dx between x1 and x2 is the probability that the event is between x1 and x2. If that is the case, then the cumulative distribution function is simply the integral from minus infinity to x of p of x dx. So the cumulative distribution function at x gives us the probability that, or let's call it x1, probability that x is less than x1. So it actually accumulates probabilities from 0 to 1. Of course, the cumulative distribution function at infinity is going to be 1. So we will use the cumulative distribution function of the Gaussian. It has several very nice statistical properties. We will not discuss all those here. So let's move ahead to the Gaussian. Before we move to the Gaussian, I just want to recollect what we looked at, the sums of random variables in the previous video. Remember that expectation of two different random variables simply sums up as expectation of x plus expectation of y. Variance of alpha times x is alpha square variance of x, and variance in case two events are independent also adds up. Variance of x plus y is variance of x plus variance of y. So we will use this in what follows. So I just wanted to recollect that. So let's come to the Gaussian distribution. This distribution is a very standard probability density function, and it has the following expression. You can see this here. F of x, which is the Gaussian PDF, is given by 1 by square root 2 pi sigma. What is sigma? Sigma is the standard deviation of the Gaussian distribution, or you can see simply mu as sigma as two parameters of the Gaussian, okay, of that PDF of the Gaussian. Just like A and B were two parameters of the arbitrary function that I wrote out in the previous video, similarly, you can see mu and sigma. But why did we choose mu and sigma and not something else? That's because there is this nice shape. The Gaussian peaks at whatever value of mu it is. And it turns out that the standard deviation of the Gaussian is exactly sigma. So mu for the Gaussian happens to be the mean. It also happens to be the median. It also happens to be the mode of the Gaussian. So Gaussian has this unique property that mean equal to median equal to mode. So to recollect, mode is the value which is the most frequent. Of course, it's not really fair to speak about this for continuous distributions, but you can see that if I drew a histogram, then the Gaussian would peak right around mu. You can also see that it's the median in that 50% of the values are below the mean and 50% of the values are above the mean. Mu also happens to be the expectation. That is, if I take this function f of x and I do integral of x, f of x dx from minus infinity to plus infinity, it turns out with this expression, all the sigmas will cancel out and it will come out to exactly mu. Okay, so that's why this is defined that way. Now, what about sigma? It turns out that the variance of x, where x is drawn from the Gaussian, is actually exactly sigma square. So sigma is the square root of the variance of x for the Gaussian. There are other further properties which you would have also seen earlier. If you have not, let's take a brief look at it within this video, which is that within plus or minus sigma, 68% of all values are covered. Okay. So for example, let's look at the heights of adult males. So if I look at, let us say it approximately looks like a Gaussian, then if I look at the mean height plus minus one standard deviation, usually 68% of men's heights will come within that. Now, if I take mean plus or minus two standard deviations, and this is really what enables a lot of polling. We'll say with 99% confidence, we think that XYZ will get so much percentage of the votes. The reason they say it is with this. So you take the mean number of votes, look at the standard deviation of those votes, and let's say they lie on a Gaussian, then mu plus or minus 2 sigma covers 95% of the value. So this is a very useful number. 95% is always plus or minus 2 standard deviation. So you can take a reasonably small sample and actually guess about 95% of the variance of what is happening, provided your entire distribution is a Gaussian. Of course, mu plus or minus 3 sigma gives you 99% of the value. And you might have heard the word 6 sigma. So mu plus minus 6 sigma covers all but a millionth. Okay, so when they talk about mu 6 sigma, what they mean is they want accuracy such that only 1 in a million cases will fail. Okay, so that is 6 sigma accuracy. So this is extremely useful for all sorts of random experiments. That is because even if the individual distribution is not Gaussian, the normalized sum of identically distributed, remember that term IID again, independent identically distributed random variables with finite variances will tend to a Gaussian distribution as the number of variables grows. So I don't want to discuss this too much. This requires a full course in statistics, or at least it's usually a part of a full course in statistics, and we are relegating almost all of probability and statistics to just this 1 week. So obviously, I cannot discuss this in detail, but this is the reason why you will see this kind of Gaussian coming again and again, starting from quantum mechanics to solid mechanics to fluid mechanics. the shape haunts us again and again, and we will use it again next week also. Of course, Gauss, who was the person, incidentally, who came up with the least squares, who also came up with this distribution. Okay. Now, if you look at this, this has two parameters, mu and sigma. Now, it turns out that just like similar triangles, you can make similar Gaussians. And we standardized a Gaussian to what is called a standard normal table. And that standard normal table, or the standard Gaussian, looks like this. The mean is at 0. And one standard deviation is 1. So 68%. The values lie within 1. So this is just a scaled version of the Gaussian. Why is this useful? Because it turns out every Gaussian can be rescaled to a standard Gaussian, and we can just make the tables once and for all. And as you will see later on in this video, that helps us solve a lot of practical problems. Okay, so we use, in order to scale, we reuse this original idea here. The fact that expectation of x plus y is expectation of x plus expectation of y. And similarly, this idea of a variance also. Okay, so let's use that here. So let's say x is a normal variable with mean mu and variance sigma square, like we had in the original Gaussian table. Now, suppose I want to change this to variable z, okay, such that, so usually we denote the original one as this, the Gaussian as normal. This n stands for normal, or the Gaussian distribution, with mean mu and standard deviation sigma square. Then we will say that I want to rescale this so that z is a normal distribution with mean 0 and standard deviation 1, or variance 1. Okay. Now, what scaling of the variable will enable that? Okay. So suppose y is alpha x plus beta. Then expectation of y is going to be, by linearity, alpha times expectation of x plus beta times, there is nothing there. There is no random variable here. That expectation is basically 0. So we can actually, so this is scaled by beta times 1. Expectation of 1 is simply 1. So expectation of y is alpha times expectation of x plus beta. So let's say we want expectation of y to be 0, and alpha times expectation of this is mu. So this gives us alpha mu plus beta has to be 0, okay, in order for our rescaling. So a simple idea is we take a rescaled variable and we use the meaning that I told you. The meaning of mu is where it peaks. So I know that my original peak was at mu and I want the new peak at 0. So I subtract mu. And I know that this was mu plus sigma and I want the sigma down to 1. So I will scale the entire variable by a factor of sigma. Now what happens here? If I do this, then this means alpha is 1 over sigma and beta is minus mu over sigma. So you can immediately see that alpha times mu plus beta is equal to 0, which means expectation of this new variable z is equal to 0. Now what happens to the variance? The variance, it turns out, is variance of z is variance of alpha x plus beta. Now, we saw that the sum of the two variances can be the sum of the variances provided the two variables are independent. Now notice x is a random variable. Here there is no random variable, there is only one here. So these two are independent. So this is variance of alpha x plus beta times variance of a constant 1, which is just 0. So this is alpha square variance of x, which we had written before. Now alpha square is 1 over sigma square times the previous variance. So you basically get just 1 over sigma square multiplied by sigma square. So this is 1. Okay. So all put together, basically what you get is this new variable, the scaled variable, x minus mu by sigma is normal, of course. It has mean 0 and it has variance 1. Now, if I take a look at the previous one and rewrite this, so this becomes f of z is, we should not call it f really speaking, I'll call it phi of z is square root of 1 by 2 pi sigma e to the power, this exactly is z, e to the power minus z square by 2. So that's what I have written here. So this is called the standard Gaussian or the standard normal distribution, as I have written. So what does the standard normal distribution look like? It looks like the same thing, except of course, mu is 0, sigma is 1. Otherwise, there is no look. It's just like zooming in or zooming out and just moving this around to the left or moving it to the right. So we have moved it to the left by a value of mu, and we have zoomed out so that the net variance is simply 1. So you just scale it so that it is 1. So the point here is every normal distribution is a rescaled version of the standard normal distribution. So as I have written here, mu equal to 0 and sigma equal to 1. And that makes it very powerful. Now, why does this make it powerful? So let's look at that in the next slide. So here we see the standard normal distribution. I'll explain how we are showing it here shortly. This is from a book by Sheldon Ross. I have just taken a screenshot from that book. This is a book by Sheldon Ross, and he has written a series of books on probability, highly recommended in case you want elementary probability theory. Now, notice what is written here. What is written here is an integral from minus infinity to x, and this is capital phi of x. So what we have here is actually the cumulative distribution function. Because that happens to be very, very useful, as I will show you very shortly. It is extremely useful but the function we are using is the Gaussian 1 by square root 2 pi e to the power minus z square by 2 or y square by 2, whichever way you want to do it. So phi of z, capital phi of z is integral of, this is small phi, this is PDF, this is CDF, cumulative distribution. So integral of small phi of x dx from 0 to z. Okay, so till wherever you want, if this is the PDF, you sum it up, and that's what gives you the cumulative distribution function. So this gives you capital phi of z if this value is z. Now, why is this useful? Notice that at x equal to 0.5, the x equal to 0, CDF is 0.5, which makes sense. Okay. Why does this make sense? Because you have this. If I integrate up until this point, the integrated value phi at 0 is equal to 0.5 because exactly half of it is below 0. And if I go to phi of infinity, that should be 1. So you will see that here. as we keep on increasing in value, you'll see that about 3.5, as I told you, 99.9% of the values are filled there. You will get 0.9998. Okay, so you get a high value when you come somewhere here. So usually tables are written only from 0 to some positive value or from negative value. And there are different ways of writing this table. Within the exercise, I asked you to look at a standard Gaussian table. You don't need to take a look at only this. You just put standard Gaussian table. You will find a million of those if you search within Google. Okay. So coming back here, let us say I have a variable. This is the unscaled variable. This becomes clearer when we look at an example, but let's say this is an unscaled variable, the original variable. Let's say I have drawn Gaussians of heights. So I want to find out what's the probability that any person is lower than, let's say, 4 feet high. Okay. An adult male is lower than 4 feet. So this is X. This is the value. This is the variable X. And this is the value X1, which we are trying to make this lower than. Now, instead of writing a Gaussian in terms of X with the specific mu and sigma that we have, we scale it. We say that instead of doing X less than X1, I will instead transform this to Z less than Z1. Okay. So where Z is subtract mu from X and divided by sigma. So this is Z. And similarly, Z1 is subtract mu from X1. So X1 minus mu by sigma is Z1. Again, like I said, easiest to see this in an example. Now, when I want to find out when is X less than B, all I need to do is to find out where this value. Okay. So this cumulative distribution function, if I can find out, this is capital phi of Z1. So I locate the point this stays at and then simply look it up in this table. And this is a standardized table. Okay. This is a standardized table. You look it up there. Similarly, if I want the probability that X1 less than X less than X2, all I do is I transform this into another equation, Z1 less than Z less than Z2, where Z1 is X1 minus mu by sigma and Z2 is X2 minus mu by sigma. And Z is, of course, the standard normal table. Now, how do we find out this is probability that Z is less than Z2. This is probability that Z is less than Z1. Now, why does this work out? Suppose I want the probability that Z lies between these two variables, Z1 and Z2. Probability that Z lies is less than Z2 is given by capital phi of Z2. That's the area under this curve. Similarly, the area under this curve shown here, let me color it in a different color. Let's say pink. This area is phi of Z1. What we actually want is all this area in the middle, which is capital phi of Z2, which is this whole area, minus capital phi of Z1, which is this restricted area. So the area in the middle is given by phi of Z2 minus phi of Z1. Now, if we want for negative values, okay, so all we need to do is to flip the table and we can find that out by symmetry. So let me show you a couple of examples of this and then this entire thing will become a little bit clearer. So let's see an example now. So let's say X is a normal Gaussian random variable. with mean equal to 3 and variance equal to 16. So I'm asking you to find out the probability that x is less than 11. Okay. So if you were to do it without the scaling, what it will look like is you'll first draw the Gaussian, and the Gaussian will be centered around mean equal to 3, and its standard deviation will be, in this case, sigma is 4, variance is 16, so sigma is 4, so plus 7, minus 7 means minus 1. And then you would have to integrate this area of x less than 11. Now you will have to do this integral. Okay. Now, how do you integrate this? You have to integrate that PDF again, the complicated looking PDF with e to the power minus x minus mu by sigma whole square. Now, instead of doing all that, we rescale. We rescale the entire problem and pose it in terms of that. So we rescale the exact problem to say all problems will be turned to problems with z. Mean is 0, standard deviation is 1. And I will map each one of these x's into this location. So let's look at it. So this is x is less than, let's say, some x1. And x1 is 11. Mu is 3. Sigma is 4, which means the corresponding z1 is, when we ask corresponding z1, really speaking, what we are asking for is how many standard deviations is this value away from the mean? How many standard deviations up am I looking at? Okay, really speaking, that's what we are asking. So x1 is x, z1 is x minus mu by sigma, which is 11 minus 3 by 4, which is 2. So in some sense, what we are asking is how many of these values are below 2 sigma, okay, starting from minus infinity. So what we have to look at here is P, that Z is less than 2. Now we have turned it to a problem which simply says the proportion of things which were less than 11 in the original graph. Okay, remember mean is 3 and standard deviation is 4 there, is the same as the proportion of things, since we are looking at probability, which are lower than a standard deviation of 2, or sorry, a value of 2 within the Z table. So for this, of course, we need the integral, and the integral is denoted by capital phi. There is no analytical value there, which is why we write it as a table. Capital phi of Z 2. So this is P of Z less than 2 is capital phi of 2. So that's what we need to look up within the standard normal table in order to find this value out. So let's look at that value now. So here is our standard probability distribution table. The way to read it is, I want an x or a z of 2. So I'll come down here and look at 2. And it's 2.0, it's not 2.01. If it was 2.01, I would have come here. If it is 2.02 here. But since it's just 2, I just look at it here and this is what I get, 0.9772. So 0.9772 basically means that the probability that x is less than 11 is phi of 2, which is 0.977. The second question is, what is the probability is that x is greater than minus 1? Okay. So once again, let's look at the reference graph. The reference graph is, we had 3, 11. You don't need to draw this. I'm just drawing this because if some of you are unfamiliar with this. So this is just one standard deviation below will actually give you minus 1. Okay. So in the original graph, because remember, the standard deviation was 4. So 3, 7, minus 1. Whereas in the Z table, so let's say Px greater than x2, which is the same as be Z greater than Z2, the same proportion of objects, provided we map it correctly, are going to be located there. So just as an example, instead of calling my dice 1, 2, 3, 4, 5, 6, suppose I call it 1 by 7, 2 by 7, 3 by 7, 4 by 7, 5 by 7, and 6 by 7. That still doesn't change anything about how many times I'm going to get 1 by 7. It is still going to be the same value as before. I just rescaled the basic, what I call the basic values. And that's the cleverness in this trick here. So if we come down to this, Z2 is X2, which is minus 1, minus mu divided by sigma. So this comes to minus 4, this minus 1. So basically one standard deviation to the left. So we want P Z greater than Z2, Z greater than minus 1. So in terms of the graph, the Z graph, this is minus 1, this is 1. We are looking for this area. Okay. We are looking for this area. Now, there are multiple ways of calculating it. One way of calculating it is like this. I'm going to show you one way here. You can choose to calculate it in many other ways if you wish. I'll calculate this area. So I'll calculate this as 1 minus probability that Z is less than minus 1. But of course, I don't know that area also. I'm going to now calculate that area as same as. So I'm doing this in a convoluted fashion just to show you the different ways in which this can work out. So this is exactly the same as 1 minus probability that Z is greater than 1 by symmetry. Okay. But probability that Z is greater than 1 is 1 minus probability that Z is less than 1. Does that make sense? So I hope you can see that this is exactly the same as probability that Z is less than 1. Okay. Again, you can do this directly through symmetry. So this might look like an unnecessarily convoluted calculation. I can show it to you in another way. So I wanted the probability that Z is greater than minus 1, which is this probability. By symmetry, you can see that this is exactly the same as this area. So this is probability that Z greater than minus 1. This is probability that Z is less than 1. So the two are the same, which basically is phi of 1. So if you see phi of 1, it's here 0.8413. So you can say that this probability is 0.8413. What probability? The probability that X is greater than minus 1. So finally, we have the third part, which is probability that X lies between 2 and 7. So let's calculate that now. We'll use the same trick as before. We'll say probability that X lies between X1 and X2. So which is the same as the probability that Z lies between Z1 and Z2. Z1 is 2 minus 3 divided by 4. And Z2 is 7 minus 3 divided by 4. So this basically gives us probability of minus 1 by 4 probability 1. Okay, sorry, not probability of 1 by 4. Minus 1 by 4 and 1. So we basically want the location that probability, or let's say write it more accurately as Z lies between minus 0.25 and 1. Okay, so once again, let's draw this for reference. Minus 0.25 here, 0 is the mean, 1 is a little bit later, and I want this area. So the way to find out this area is to say this is the same as phi of 1 minus phi of 0.25 minus phi of minus 0.25, sorry. Okay, phi of 1 is straightforward. We just calculated it. Phi of 1 is, we can see that here, 0.8413. Okay, but what about phi of minus 0.25? So phi of minus 0.25 calculates this area here. Now, how do we calculate this area? Okay. So what we can do again is by symmetry, we can draw phi of 0.25 and say this area here is going to be exactly the same as this area here. Now, what is this area here? This area here is 1 minus phi of 0.25. So we can use this relationship that phi of minus x is equal to 1 minus phi of x. And that gives us, this is 1 minus phi of 0.25. What is phi of 0.25? You can come back here, 0.2, 0.25, 0.5987. Okay. This is 0.1 minus 0.5987. So overall, we have 0.8413 minus 1 minus 0.5987. So if you calculate this, this comes to 0.4400. So the point of this exercise was to show that you can take variables with some mean and some variance and rescale them so as to be able to calculate it using the standard Gaussian table. Now, I want to use this example for a slightly more practical problem, which is the next problem that we will see now. So let's look at this problem. Let's say we have a disk drive unit and we have a metal shaft. Okay. And typically after manufacturing, you are not going to get exactly the same size for everything. So you can see that after manufacturing, the mean disk drive unit diameter, the shaft diameter is 6.37 mm, whereas the standard deviation, there is some error in the machine. So you have this in micrometer. Notice this. If it was in millimeter, obviously you cannot do anything with this machine at all. In this case, you have a machine. After machining, you have a small amount of variation within micrometers. So what we want to find out is there are specifications over which this disk drive unit will work. We want to check whether how many of the things that we manufacture are going to lie within those specifications. We are told that the specifications are such that we want to be within this range. We want to be 6.35 plus minus 0.038 millimeter. Okay, so we want to check how many of the shafts that we produce actually conform to this specification. So let's write this out formally once more. So let's say X is the random variable, which is the shaft diameter. What do we know? We know mu of X is 6.37 mm. We know sigma is 12.7 into 10 power minus 3. I'm going to write everything in mm. Okay. Now we also know that X is normal with, of course, mu and sigma as our uh, mean and standard deviation. Okay. Now, what we want is X should lie between some limits. So X1 less than equal to X less than equal to X2. This is what we want. Okay. X1, of course, is 6.35 minus 0.038 mm. So X1 is 6.312 mm. X2 is 6.35 plus 0.038 mm. So that is 6.388 mm. So what we want to know is, after doing our computation, how many of the values will lie here? And the way we do it is, of course, we are going to keep the proportion the same. We are going to say same as fraction in Z1 lying between Z lying between Z1 and Z2. Now, what is Z1? The Z1 is X1 minus mu by sigma, where mu is given by 6.37 and sigma is 12.7 to 10 power minus 3, and Z2 is X2 minus mu by sigma. Okay. So now if you calculate these values, it comes out to be, so you can see X1 is 6.312 minus 6.37 divided by this 1.27 or 12.7 to 10 power minus 3. If you calculate this, this comes to approximately minus 4.56. Okay, somewhere around there. Similarly, Z2 comes out to approximately 1.4173. So once again, I always find it convenient to draw these figures. Z1 is somewhere here, Z2 is somewhere here. What we want is phi of Z2 minus phi of Z1. Now, if we go back to our normal distribution table, you can see that this is 3.5. There itself, it's approximately 0.99. So if I look at Z1, that is far more below than that. Okay, so this is minus 4.4 something. So you might as well treat phi of Z1. You can treat it as 1 minus phi of minus Z1, which is here, which is entire table. So this is approximately 0. Okay, so this is approximately 1, or you can call this minus Z1 and plus Z1, whichever way you want it. So after 4 standard deviation, nothing really survives. So nothing is going to be lower than the lower end of the diameter. Whereas phi of Z2, Z2 was 1.4173. So we can look that up here. So 1.41, or I can look at 1.42 approximately, is 0.92. So we can say that about 92% of these are going to be within the shaft specification. Now, this is very useful because you can now control the quality of manufacturing, and you can actually make some predictions about what will happen when you do manufacturing with some amount of tolerances. You can also probably guess that this kind of thing is extremely useful for heat transfer. We can say in how many cases, when you run a full app, in how many cases are you expected to actually blow up or expected to reach temperatures which are too high. Similarly, in the cases that we were looking at with this slab also, not only do we give A and B or W0 and W1, you can actually start talking about the uncertainty in the weight estimation that you have done. Instead of simply giving that these are the optimal weights or this is the flux, you can actually start saying, well, 95% of the times the flux value will lie between this and this value. Okay, so that's far more useful. So if you give mu and sigma at least, it is far more useful than just giving mu, which is what happens to be the case when we were doing our typical function fit. So what we saw in the current video was the Gaussian distribution and how you can use it to make a range of predictions in the range of probabilistic estimations. We will use all our ideas so far put together. We will use that in the next week to give probabilistic versions of the algorithms that we have looked so far. So I hope this week was useful. I'll see you again in the next week. Thank you.